We are going to cover finally the Riemann curvature tensor today and a couple issues related to it. The Riemann curvature tensor is a very large object. It's a 4-0 tensor or a 3-1 tensor, depending on how you decide to raise or lower the indices. However, in 2 dimensions on surfaces, the Riemann curvature tensor is very simple. It's just one number. It's going to end up being a Gauss curvature. So the Riemann curvature tensor isn't as complicated an object in 2 dimensions, and we're going to leave it at that. I guess the general formula will be up on the board, but we're not going to explore the general formula. Okay, so the outline is, well, we're going to go back to something that we covered a little bit earlier, which is the exponential map. The exponential map is an intrinsic object, and it involves geodesics, and we can use it to parameterize a neighborhood of a surface, parameterize neighbors of a surface. As you remember, we proved that the exponential map was a diffeomorphism near the origin. So this is going to bring us to, well, the reason I'm reintroducing the exponential map is so that I can talk about the nature of the metric in those coordinates. It turns out something quite interesting happens, and tells us, if we want to look for invariants, like intrinsically invariant objects, we have to work a bit harder. And we're going to end up at the Gauss curvature tensor, and we'll have a so-called local rigidity theorem, the theorem egregium, which is Latin for something I'll tell you about in a few slides. Anyway, it's Gauss's theorem, which describes the Gauss curvature as the important local invariant. Then we'll talk about this idea of invariance a bit more in the context of isometries. And then this will be just sort of a discussion, more or less. And then at the end, we'll talk about the Gauss-Bonnet theorem and see what that has to do with, interpret that as a local rigidity theorem. So, yeah. Okay, so these words, anyway, will make a bit more sense than I go through. Okay, so let's start at the beginning, which was material from a few lectures ago, maybe 2 weeks ago or something. So remember the geodesic exponential map of the surface. So the way this works is you have a surface and a point in the surface, and then you choose a vector at that point. So V is a single vector in tangent space at the point of the surface. Okay, and what we proved is that, well, we didn't exactly prove it, but in any case, I asserted that given P and V, there's a unique geodesic which passes through P in the direction of V. So in other words, gamma at 0 equals to P, and gamma dot at 0 is equal to V. Okay, so yeah, so we proved, well, we didn't prove it, we asserted that there exists such a thing, given P and V. And then I told you more or less what the proof, I told you the main ingredient in the proof. The main ingredient of the proof is that you have a geodesic equation. Well, I guess so you have the geodesic equation, which was that the geodesic curvature of the curve is normal to the surface. Or, in other words, that you have this family of ordinary differential equations. Not family, system of ordinary differential equations. Right, so when we took this geometric condition that the curvature of the curve is orthogonal from the surface, we wrote that down in local coordinates in a parameter domain, this green parameter domain. We got an expression which was a second derivatives, involving the second derivatives of gamma and these so-called Christoffel symbols. Okay, so the geodesic equation, as we saw it back then, is a system of ODEs, and because it's a system of ODEs, you can now quote the existence uniqueness theorem for ODEs, which says exactly this: there's a unique geodesic through P in the direction V. It satisfies the solution of these ODEs. Okay, so this was the exponential map, this was the existence of geodesics, and then the next thing we did was we defined the exponential map. So the exponential map at a point P on V was just gamma of 1, where gamma of 1 is you go a unit distance along this geodesic. You go a unit distance along that unique geodesic. So x sub p of v specifies a unique point, provided, of course, that the magnitude of v is sufficiently small, right? Because the fact of the matter of this system of ordinary differential equations, it guarantees local integrability, and if you go far enough, things might not work out. So you need the norm of v to be sufficiently small, so that so that you can, this point is well defined. But of course, the theorem that we then proved is that the differential of the exponential map at the origin was the identity. And of course, the identity is invertible. And so what that says is that the exponential map itself is invertible. Well, not exactly invertible, but let's say locally invertible. So what this means is on a sufficiently small ball, very small ball, the exponential map is a diffeomorphism. Okay? And the consequence of that is you have this nice picture. The picture is the surface over here, right? And a point, the tangent plane, and then any direction here now maps onto some point on the surface. Right? So, in other words, your exponential map becomes a diffeomorphism from some neighborhood of zero, some neighborhood of the origin in the tangent space, so 0 is in here, to some neighborhood sitting inside the surface. And it's a smooth invertible map with differential inverse. So that's this number one key fact, a reminder of the construction, and this number one key fact on the board, on the screen. Okay, so a couple other facts. Well, we did not prove this one, the second fact, but it's still true. It is that you can take these balls, these neighborhoods, U and V, you can assume that they're geodesically convex. What this means is you take any 2 points in there, you trace a geodesic between them, and it stays inside that ball. So geodesic convexity just means, well, the picture means this. So let's say U and V are convex, which is the same thing as this picture here. Here's, let's say, U, and then here's the origin, right? Here's our point X, here's our point Y, and maybe the geodesic looks like this. The geodesic looks like that. Maybe I'll make it in red. The geodesic between X and Y stays in the ball. So this is a fact about these U and V. They're geodesically convex. And another simple fact, this is not a complicated thing, this is a simple thing, is that the curves, this is more or less by construction, right? The curves, T maps to X of TV, they are geodesics. Right? This is just by construction, right? If I put T up here, it's basically the same as putting in T there, again by existence uniqueness of ODEs. It's the same curve. Okay, well, right, fine. Okay, so this is obvious fact that I can represent the geodesics through P very nicely, with this exponential map, basically by construction. Okay, so this is the reminder of the exponential map. Everything we need to know for today. So let me move to the next. Any questions about this? I'm trying to jog from memory here. Okay, let me put up the next slide and erase for a bit. Okay, right. So since we have this diffeomorphism from the tangent space to the surface itself, we can actually use this to construct coordinates. Or I guess let's say parameters. I should have said a local parametrization rather than local coordinates. So the idea is this. Let's draw a, right, let's do this. Let's do this. This is going to be R2. This is going to be the tangent space of the surface, and then over here is the surface itself. Let's put, here's P, here's the tangent space, right? Okay, how do I get coordinates? Well, what I need to do is somehow map from R2. What I need for a parametrization is I need to map from R2 directly into the surface. Okay, right, so I'm almost there. I have a mapping from the tangent plane into the surface using the exponential map. What I need is just a way of getting real numbers into the tangent plane. And then I can get real numbers into the surface, which is the definition of a parametrization. So how do you fit real numbers into the surface? Well, remember that this is an abstract vector space. Right? It sort of exists as a two-dimensional vector space. We haven't done anything like choose a basis yet. But as soon as you choose a basis for an abstract two-dimensional vector space, then it does become canonically, not canonically, sorry, it does become, what's the right word, sorry, isomorphic, let's say, to, yeah, isomorphic is a vector space, sure, isomorphic to R2. So what we do is we choose a basis. We choose a basis here, so E1 and E2. Did I use? Yes, it did. Okay, E1, E2. And so we're going to choose a basis. So you have E1, comma E2 belonging to tangent space at P and S. And without loss of generality, we can say that this basis is orthonormal. And the reason I say without loss of generality is because it's just one vector space. So you can do vector space things in that one vector space. For example, in particular, you can pick any two basis vectors that don't have to be orthogonal, and then apply Gram-Schmidt to them. And then you get an orthonormal basis. Okay? So I choose, and I'm not doing anything sophisticated like choosing tangents, choosing vectors in the entire surface. I'm just making a choice in one vector space, right in this tangent space. Okay, and so now you can take a point. Now you can take a point x1, comma x2 in R2, and you get a point. In fact, you get a vector x. I should put the ones upstairs. You get a vector x1 e1 plus x2 e2. Right? So this is how you do it. Now we have a way of putting real R2 coordinates into the tangent space and then following on with the x map. So in other words, my formula from, this is phi, my formula for phi goes from R2 into the surface, and it's phi of x1 comma x2 is the exponential map applied to that vector up there. So x1 e1 plus x2 e2. Okay, so far, so good. Something to note, of course, let's change color so it's easier to see. Something to note, of course, is that phi is defined on a small ball. Right, so this phi is not necessarily defined on the entire R2, it's defined on some small ball. Some radius r is sufficiently small so that the small ball maps into the domain of definition of the X map, and then we're good to go. Right? Okay, right. So a couple of interesting observations about these coordinates, going from simple to most complicated. So the first simple thing is that in this coordinate system, in this parametrization, I should say, for a small neighborhood of P, straight lines in the parameter domain. This is the parameter domain now. Straight lines in the parameter domain. This is a straight line here, right? This is t times x1, x2, where t varies. Let's just put t in the reals. T varies, right? Maps to a straight line in direction x1, e1 plus x2, e2 in the tangent space. And remember we said on the previous slide is that x of tv is a geodesic. So that straight line here maps to this geodesic here, let's say. This is a geodesic. Okay, so, right. Straight lines through the origin map over to geodesics. So in particular, the coordinate axes, the coordinate curves themselves are geodesics too. Okay, so question for you guys. What about this curve here? What about a straight line which is parallel to the one I just drew? Or in fact, any other straight line which is not running through the origin? Can you make any statements about that? So, yeah, let's say it's as close as it needs to be, and let's say this one here is vector v plus t of, let's say, x1, so v0, some shift vector, right? And so then your geodesic, not geodesic, your curve is xp of t times v0 plus x1, e1 plus x2, e2. Sorry, the t goes here. That's the curve that I'm mapping forward. This dotted curve is mapped forward by that, and so the dotted curve is somewhere like this. So what can we say? Can we say anything about that curve? Well, not really. I mean, you might be lucky that it's a geodesic, but this form for that curve doesn't necessarily make it a geodesic because of this shift offset vector, right?
Where does it violate the geodesic?
It doesn't satisfy. So this problem, this is it actually. So this thing here doesn't satisfy the geodesic equation, I guess. Like the x sub p of TV, what is this really supposed to be? It's supposed to be a solution of this equation such that gamma dot at 0 equals to v, and gamma at 0 is equal to some point, not necessarily p, but let's say w and q. It's supposed to satisfy this equation, and this derivative here doesn't satisfy this equation, right? This is, and the t's in the wrong place for it to satisfy the equation. I guess I'll have to maybe write that out a bit more carefully later. But in any case, the t is in the wrong place. And so by definition, the t needs to be in the right place for this thing to satisfy the differential equation by definition of it. Anyway, I guess I'll have to write that out more carefully later, so I'll do that afterwards. In any case, I just want to point out that you do have a nice form for some of the geodesics, but not all of the geodesics. So in particular, the geodesics of the neighboring geodesics might be arcs. Right? They might be arcs. The ones to the origin are straight lines, but the neighboring geodesics might be arcs. Okay, so let's put here not geodesic. Okay, right, so that's the first point. Now the second point, well, the second and third point on that slide actually refer to the form of the metric tensor, or the induced metric, the intrinsic metric, right? So there's Gij. So I'm claiming here that Gij is delta ij, which means 1 or 0, depending on if I or j are equal to each other or not, plus no first order terms, and then only stuff starts to happen at second order. So what this means, so this is like the Taylor series of the metric tensor in the parameter domain. Okay? And what we're saying is that the 0th order term is the identity, is the Euclidean metric, the identity metric, 1, 1, diagonal. The derivatives are 0 at the origin, and only later you start getting stuff. So second derivatives are non-zero. But the first derivatives and the metric itself are very simple, Euclidean and 0. So let's explore both of these things here. So point number 1, so I need to do a bit of erasing. So point number 1 actually is straightforward because we've already proved something important, which is that we've already proved the necessary ingredient, which is that the derivative of x at the differential of x at 0 is the identity. So what that means is that the so we have E1. So we have right, so phi of x is equal to the exponential at p at x1 e1 plus x2 e2, right? So so this d phi by dx, let's say 1 at 0, comma 0. Well, this really ends up being d of x at p at 0 acting on the vector. So the 0 goes down here, is acting on the vector E1. And d phi by dx2 at 0, comma 0 is d of the differential of the exponential map at 0 acting on E2. Okay, so E1, E2. Because we proved 2 weeks ago that the differential of the exponential map is the identity, we can just say this. And of course, we already chose EI, comma EJ equals to delta IJ. This was our choice that we made at the beginning when we constructed these coordinates. We decided to choose an orthonormal basis trivially, we can easily do this by Graham-Schmidt, in the tangent plane at P. And so, of course, then you have Gij at 0, which is the inner product of d phi by dxi with d phi by dxj. That's just delta j. Okay. So it's our original choice that guarantees this. So this part is somehow not surprising. We kind of rig things up so that the metric is Euclidean in the tangent plane itself. The second point is a bit more interesting. Okay? Second point is a bit more interesting. So I'll prove the second point now. All right? Okay. So for the second point, what we want to show, of course, is that dGij dxk equals to at 0, 0 equals to 0 for all I, j, and k. Right? I want to show that the second term in the Taylor series vanishes. All right? How am I going to do that? Well, instead, what I'm going to show, I'm going to show that the gamma ijk's equals to 0 at the origin. So again, it's 0, 0 equals 0 for all ij and k. And this is going to be good enough. Why is it good enough? Why is this what I need to do?
Can you remind what gamma is?
Oh, I'm sorry. The Christoffel symbols. So the Christoffel symbols were, so this here was take the covariant derivative of EI with on EJ, EI with EJ, and this can be expressed as some linear combination. I mean, this is a tangent vector, so therefore it can be expressed in terms of the basis of the tangent space with some coefficients, and those coefficients are the Christoffel symbols. So I'm going to look to prove that the Christoffel symbols are 0. Now, why is this good? Why is this good? I want to show that the metric derivatives are 0. And instead I'm telling you, let's go ahead and show the Christoffel symbols are 0.
Yeah, the coefficients are the basis. The coefficients are all the coefficients are 0.
Well, not quite, actually. You're probably saying, you probably know what's going on here. But you didn't say it quite right, which is, I'm capable of relating this to this. Yeah?
It's the same basis that we are talking about. So if all the coefficients are 0, it makes it
So right. So I guess the key thing is the so-called fundamental lemma of Riemannian geometry, which is that you can relate these two. These two guys are related to each other. So remember that gamma ij upper k is equal to 1/2 GKL. This is a nice formula to remember. And then dgil dxk plus dglj dxk, or not k, ij, and finally minus dgij dxl. So there's a relationship between the two, which is this fundamental theorem of Riemann geometry. So if I show that these guys are 0, then, hang on, our formula goes the wrong way around. Now what? I want to show that, right, so what this formula allows me to do is that if these guys are 0, then those guys are 0. Okay, that's not quite what we wanted to show. We wanted to show that if these guys are 0, then each of these guys individually are all 0.
It's a linear combination, the matrix should be invertible.
Yeah, the matrix should be invertible. Yeah, exactly right.
Because the basis is orthogonal, or in case it spans the graph.
Yeah, right. So really, this relationship is true, but it's also an invertible relationship. So you just want to find it the other way around. So in fact, you want to find, you're going to find dgij dxk. Well, this is equal to d by dxk of the inner product of EI with EJ. And now you use the, well, this I guess is E sub k, right? So now you use the metric property of the covariant derivative, right? This derivative on the outside comes in via the product rule. So you have this, EI comma EJ, plus EI, and then covariant derivative in EK of EJ. And that is equal to, well, it's equal to gamma lower I, gamma lower Kij plus gamma lower Ikj. And the gamma uppers, or the uppers are related to the lowers by means of an invertible matrix, so you're good. Okay? So So you do have this invariable relationship between the derivatives of the metric and the Christoffel symbols. Okay, so that's why it's good enough for me to show that this Christoffel symbol derivative, these Christoffel symbols vanish. Okay, so that still brings us to actually doing that. So how on earth do you make that happen? Okay, well, it turns out there's a very cute trick. I mean, if ever, we haven't, yeah. Occasionally there's some cute tricks in math, and this is one, in my opinion. Okay, so look at this number, look at this line right here. Straight lines through the origin in the parameter plane are geodesics. So what this means is that what that means is that. Think about that for a second. Okay, so if I draw this out, here's my parameter plane. Here's V1, here's V2, let's say. So what I have is all along here, I've got V1 equals to 0. All along here, I've got del V2 equals to 0. Right? I choose a third direction. This is V3. All along here, all along that curve, I've got del V3 equals to 0. Right? I can make, because these oscillators are all geodesics, right? And that's the geodesic equation. Right? So, yes, this is the geodesic equation. Right? So along the geodesic equation holds. And the geodesic equation along the V1 geodesic is del V1 equals to 0. Along the V2 geodesic is del V2 equals to 0. Right? And so on. Now where do all those geodesics coincide? They coincide exactly in one place, right at the origin. And at the origin, you have all of these equations simultaneously holding. Right? So in other words, you have del V equals to 0 for all V at the origin. So this needs to go into a box. And this needs to be emphasized right here. But this is true at the origin. It's not true everywhere. It's true at the origin. Okay? Make sense? Okay, now watch this. This is the cute trick that I was telling you about. Let V be EI plus EJ. Let V be EI plus EJ. Okay, so what you have is del EI plus EJ acting on EI plus EJ equals to 0. Now you expand this thing. Use the rules of covariant derivatives to expand this thing out. You get del EI plus del EI EJ plus del EJ EI plus del EJ EJ equals to 0. Okay, now what? Yeah. Yeah. Okay, so this is gone by the equation we wrote before down there. This is also gone. Can anything special happen here? Is it true? Can you switch the order of covariant differentiation? Well, this you can actually. Remember that so we didn't discuss this too carefully because in class. We left it for a supplement because the torsion property, the torsion-free, I should say, property of covariant derivative is that del xy minus del y, or equals to del yx plus a Lie bracket term. And of course, if you apply this to EI, EJ, then you get that equals to EJ, EI, plus the Lie bracket of EI and EJ. And what we argued, at least back then, and also the supplementary material, is that this is 0 because EI and EJ are coordinate vector fields. Because EI are coordinates. Okay, so what we have is EI, EJ equals to EJ, EI. And so therefore, this equation becomes, well, 2 times, but del EI, EJ equals to 0 at the origin. And that's what we set out to prove. Aristotle symbols vanish. Well, this vector vanishes, but of course this vector is equal to, by definition, the linear combination of Aristotle symbols, so therefore those Aristotle symbols have to vanish. Okay, so this implies all coefficients. In other words, gamma ij k equals to 0. Okay, so we've now done it. We've now established this formula, which is the Taylor series expansion of the metric to second order in the geodesic normal coordinates. Okay, so some conclusions to be drawn from this. Okay, this brings us into the topic of rigidity, which I'm going to divide into 2 things, local and global. So right now we're working in a neighborhood of a point, so this is always local. So now so this brings up local rigidity. Okay, so what we've done is we've found coordinates that make the induced metric Euclidean near a point, or in fact at a point. Euclidean to second order at a point. And the question, one of the early questions in differential geometry, in fact, which motivated Riemann, was, can you do better than this? So, can we achieve something between the ultimate and, well, maybe the next step? So the ultimate would be, you have this manifold, you have a metric on it, and it projects down to something or other, in the parameter plane, and that metric is non-trivial. So the question is, can you change coordinates in that domain to make the metric Euclidean everywhere, completely trivial, Euclidean? And let's say the answer was long suspected to be no, because it's the map maker's problem, right? What is a map? A map is a map of the Earth. The Earth is a sphere, non-flat geometry, and a map is a parametrization of some part of the sphere. And all maps have these discontinuities. The edges you wrap around, right? So it's a parameterization of some open subset of the sphere minus a cut somewhere. So the question is, can you find a map which doesn't distort lengths? Right? So that's basically what you're saying. If you want to make the metric trivial in the parameter domain, that means measuring lengths on the surface is equivalent to measuring lengths using Euclidean distances in the parameter plane. So the question is, can you build a map, or can you construct a map for which there's no distortion of lengths? And people have been trying to make maps for thousands of, let's say, several hundred years. And no one ever succeeded in making a non-distorting map, and so the answer was pretty much certain that the answer to this question was no. But it was never proven mathematically, so this language that we just developed about measuring lengths on the surface and so on allows you to tackle that question in a mathematically rigorous fashion. And so the question is, can we do better than what we just did? Can we make a map? Can we make a parameterization of the surface in which the metric is completely Euclidean? So probably not, but maybe we'd like to know why not. Okay, so that's the ultimate. And then maybe the next best step is just, can we build a parameterization that improves our Taylor series expansion, that makes more of the metric 0, more terms in Taylor expansion 0? Maybe the metric is non-trivial, but maybe it is non-trivial at some high order of Taylor series. So these are the questions. And the answer to both of those questions is in fact no. So, okay, so how do you tackle this? Okay, so how do you tackle the map-making problem? We're not going to do this in detail. like 15 pages of derivation which goes between here and here. If you're interested, you can find it in Spivak's 5-volume series of differential geometry textbooks somewhere in the middle. No, somewhere in volume 1, and probably either volume 3 or volume 1.
I think 1 is metric geometry.
But 1 could potentially be an entire volume of definitions.
Yeah.
Setting up the problem. But in any case, it's in Spivak, and it's actually got a very nice discussion about it. So in fact, what's worth reading are the discussions, because they're really quite intuitive. Anyway, the way it works is, you write down equations. You have your equations, the unknown in these equations is the parametrization, and you write down equations for it. And those equations are basically transform the metric using that parametrization and set it equal to delta ij. Because that's what we want our parametrization to achieve. Metric transforms into delta ij. So it turns out those equations are overdetermined. There's 2 unknown functions, the parameterizations, and there's lots of equations. There's 3 in dimension 2, right? Overdetermined equations. So whenever you have a system of overdetermined equations, the next thing you do is you try to find out what are the solvability conditions for those equations, right? If the equation is ax equals a linear equation, ax equals to b, what you check is that b is orthogonal to the co-kernel of a, right? So there's integrability conditions involved in deciding when you can solve an overdetermined system of equations. And it turns out the integrability conditions are really quite interesting and complicated. And we can already write them down. We know enough technology here that we can write them down. They're these. They're expressed in terms of the derivatives of the Christoffel symbols and then some second order terms in the Christoffel symbols. So Riemann, I'm not sure if Riemann discovered this, I can't remember, but it is discussed in Spivak, who discovered this. But basically you follow this long derivation, really quite long derivation, and you come up with these interesting formulas involving, well, Christoffel symbols, but really these are derivatives of the metric. So let's say this is second derivatives of the metric. So some interesting combination of second derivatives of the metric has to vanish if you want to solve the mapmaker's problem. That's the integrability condition. Okay? So the local rigidity involved is this here somehow quantifies the local rigidity. A curved surface is rigid, you can't flatten it out, and the rigidity is encoded in this. And if this is 0, then the surface is sufficiently flexible that you can map it out. Okay, so let's interpret this object here. Let's interpret those conditions. So the title of my slide is Gauss's Totally Awesome Theorem, because apparently that's my favorite translation of Theorema Egregium from Latin to English. Okay, right. So we can, right, so what's the point? Well, so now I'm skipping several, like 50 years worth of differential geometry history here, because it wasn't immediately discovered like this. It was put in this form much later. So what you do is you define the Riemann curvature tensor. This object right there. The input is 3 vector fields, x, y, and z. The output, or 3 vectors, x, y, and z. 3 vector fields, x, y, and z. And the output is a vector field, is a single vector field. Right? The z is a vector field. You take one covariant derivative, you get another vector field. You take another covariant derivative, you get a vector field. So each of these objects is vectorial. Right? So that makes this thing a 3, 1 tensor. 3 vectors go in, one vector comes out. So this is the Riemann curvature tensor. And, well, you want to expand it on a basis. So expanding on a basis means, well, writing it in this form, but this is complicated tensor notation, never mind. All I want to do is figure out, I want to put in E1, E2, E3, I want to put in the basis vectors here. EI, EJ, EK, I'll put the basis vectors in there, and I'm going to see what comes out. And I'm going to express what comes out as a linear combination of basis elements, ELs. So then I get, for every choice of input, I, J, K, I get a linear combination of outputs, S, ES. Okay, well the remarkable thing, well I mean it isn't remarkable because this is the way the field was developed, but in any case, we sort of sell it to you as a remarkable thing. But in any case, the remarkable thing is that the right hand, these objects, these coefficients, are exactly the those integrability conditions. So the Riemann curvature tensor holds the integrability conditions.
Can we give an intuition for why the Riemann curvature tensor looks the way it does?
I can give an alternate intuition, but to me this is somehow my intuition. Why does it look that way?
Why are we combining all these covariant derivatives?
Yeah. Like, to me the most compelling explanation of the Riemann curvature tensor is that you have these integrability conditions, the story that I've been telling so far. There's something else that people use to explain why the Riemann curvature tensor should look like that. And it's that in Euclidean, so you say in Euclidean space, this equals that. So partial derivatives, second partials commute. So let's put EI here, let's put EJ here, let's put EJ here, and let's put EI here. Because it's not true if X and Y are functions, then you have a variable, it's not quite true. So yeah, so in Euclidean space, second partial derivatives of functions commute. So that, d squared f dxi dxj equals to d squared f dxj dxi. That's true of functions, and that's more or less also true on surfaces as well. The Hessian, the covariant Hessian is also symmetric like that. But the point is that second partial derivatives of vector quantities commute in Euclidean space. And so what this Riemann curvature tensor is supposed to do, so in non-Euclidean space, and the definition in this case of a non-Euclidean space is that the Riemann curvature tensor is not identity equal to 0. In non-Euclidean space, you have that this measures the failure of commutativity. Of EI, EJ minus EJ, EI. So that's somehow that's a different way of proposing an intuitive understanding of what the Riemann curvature is supposed to measure. It's supposed to measure the failure of commutativity of this thing. A third interpretation is down here, more geometric, but this is, we'll get to in a second, but this is somehow another interpretation for why the thing looks the way it does. Notice that, look here, EI, EJ minus EJ, EI. That's what you get when you plug in EI and EJ into this formula. Because remember, the Lie bracket of covariant vectors coordinate vectors is 0. So did you have another idea in mind?
No, not really. It's just one of these counterintuitive things that pops up.
It's definitely counterintuitive. But I guess this is because it comes from a particular starting point, which is this map maker's problem and so on. And even here, the map maker's problem, as I described it on the previous slide, or in my previous discussion, is evident. Because how do you find integrability conditions of a first order equation? Well, you check to see that second order derivatives commute. So somehow the process of finding integrability conditions involves checking commutativity of second derivatives. So anyway, it's somehow related to this even from this point of view. Okay, the third. Yeah. Okay. So sorry. We're not here yet. We're still not there. Okay. So the third. No, sorry. I didn't want to say that. Right. I want to add something here. So I could derive this for you. It's quite actually reasonably straightforward to derive this. But this yields this. Reasonably straightforward to derive. But what you do is you plug in EI, EJ, and you start expanding things. You use the Christophersons and so on. It's a straightforward computation. I was going to do it here, but I think I'm running a bit short on time. So I'm going to move it to the homework assignment. Sorry. It's a good computation to do. Okay, so that's points 1 and 2. Now the third point, actually, on this slide, is actually a third interpretation for what the Riemann curvature tensor is all about. And that was discovered by Gauss. Not in this form, because he didn't quite know about Riemann curvature tensors just yet. But he came at it from a different way. But in any case, the theorema egregium, or the totally awesome theorem of Gauss, is a relationship between this Riemann curvature tensor, which is defined in terms of integrability conditions, something pretty abstract, and something very concrete, namely the second fundamental form, which is good old-fashioned, put your hands on it, curvature, right? This is very geometric. The left-hand side is the curvature tensor, the abstract thing. The right-hand side is something very geometric. It's the second fundamental form of the surface. Okay, so I'm going to derive this formula for you. All right? We are running a little short on time, but that's okay. Okay, so how does this formula actually work? So let's say, okay, so what do you do? Well, the starting point actually is, okay, sorry, let's let this be my setup is, here's the surface S, here's some point P, we don't really need the point P, but in any case, yeah, here's some surface S. It's sitting inside Euclidean space, right? And so therefore, it has a second fundamental form. Has a second fundamental form, A, and if I introduce this to be the covariant derivative operator, in other words, just ordinary differentiation in R3, ambient space. And nabla here is covariant differentiation on the surface. Remember that what we have is that if I'm here, I have an x, I have a y, x and y are tangent. What I have is that the ordinary Euclidean space derivative breaks up into two pieces. The Euclidean space derivative, the parallel part, plus the Euclidean space derivative, the orthogonal part. And of course, we define the first bit to be the intrinsic covariant derivative. And the second part we defined as we noted, or we actually defined it earlier, as the second fundamental form times the normal vector field. Right, so there's a normal vector field here. Right? Okay, so this is what we have. When we put a surface in Euclidean space, you have two ways of differentiating vector fields: the Euclidean one on the outside, and the intrinsic one, and they're related via these nice formulas. Okay, well, that brings us here actually. So, I just have to do it from my head here, I guess. I left my note on this at home. Okay, so the way it works is you say 0 is equal to the inner product of Euclidean derivative in ej direction, ei, ei ek minus Euclidean derivative ei, Euclidean derivative ej, ek, inner product with el. That's the starting point for Gauss's theorem. This line is the starting point for Gauss's theorem. And this line is very simple to understand, right? Because as we just discussed, this is second derivatives. Second derivatives with a minus sign. So it's checking the symmetry of the second derivatives in Euclidean space. So ordinary second derivatives.
What is the head?
I'm choosing I'm making a choice of 4 basis vector fields. Basis vectors.
And they are, so it's linearly independent.
Well, it's on a surface, so it's going to be some choice of E1 and E2. So EI, EJ, EK, and EL are some combination of E1 and E2.
So they are not linearly.
No, not linearly independent. On a in higher dimensions, I could choose them linearly independently, but I'm on a surface, so it's just, I'm just going to write them down in this way. So you will later you make a choice of where to put E1 and where to put E2. Okay? Right. So what do you do now? Well, now you insert this formula where you can. So in other words, right here. So this becomes 0 equals to the derivative of ej direction of intrinsic derivative ei ek plus second fundamental form ei ek in the n direction, and then minus Euclidean derivative ei acting on intrinsic derivative ej ek, ej ek plus second fundamental form in ej ek times the normal vector, and then comma el close that bracket. So I stick in the formula where I need it. Okay, and now you do the same right here. Okay, so I guess you're going to be looking at here. Okay, I guess, yeah. In the interest of time, I'm going to abbreviate this. I'm just going to show you how the calculation continues. So I'm going to look at this piece right here. Look at this piece, and let's move it up here. And so now what I need to do is expand the derivatives one more time. Right. So what do? I do this. I go. Of course, there's a bracket, comma, EL for that first piece. So I guess I'm going to include this in the first piece as well. Okay. Does everyone see what I did? There's three. Sorry, here.
Why is there still a bar in that dude?
This one here?
Yeah.
Because there was one here.
Yeah, but you
I just didn't change it.
Didn't you expand that bar so that bar should disappear?
On the inside, I expanded on the inside. I didn't expand on the outside. Yeah. So the inside bar derivative became an intrinsic derivative plus second fundamental form. I just left the outside bar derivative alone. So the outside bar derivative is here, and so that's the first term. The second term is a product of two things. It's a product of A and N. So if I have a derivative of a product, so EJ acting on A is the directional derivative. This is the directional derivative right here. So I apply the E onto the first part, multiplied by the vector, and then plus the first part times the derivative of the vector. Okay? Right. And I'm taking the inner product with EL, which is a tangent vector. So let's see what happens. Well, in the first line, I get this. I get, without the bar, EI, del EI without the bar, EK, comma, EL. Because the difference between with the bar and without the bar is the parallel part. And I'm taking an inner product with a tangent vector field, so that's good. My second part is 0 because it's a normal vector against a tangent vector. And my third part actually is minus So there's A, E, I, E, K, and then there's an A of E, J, E, L. And that's by definition. Because remember, we defined the second fundamental form as the derivative of the normal vector field in a EJ in a tangent directed EL. We put a minus sign up there because that was like I mentioned. Okay, so you see what happens. The simple mixed partial derivatives vanish, second partial derivatives, partial derivatives from second partials commute implies this formula here. And now a similar part for the second term, right? And you're going to get the curvature tensor coming from the difference in the intrinsic parts, and you're going to get the leftover bit is going to be this bit right here. So there's Gauss's theorem for you. It follows from, let's call it the integrability condition in Euclidean space, leads to this connection between intrinsic curvature and honest to goodness curvature, extrinsic curvature. Make sense? Okay, I'm going to move to the next slide, just to give an interpretation of this. So what I want to do is, I want to lower one index so that I get the Riemann 4-0 tensor, just so I get a nice looking form for the thing. Okay, so if you go back to this formula, well, if you go back to my previous formula on the previous slide here, this is Rijk, right? And as Hardik said, I, J, K, and L they can't be linearly independent because we're on a surface. It's 4 vectors, and my surface is 2-dimensional. So that means I have to choose I, J, K, and L together, 1 or 2. And you can check the previous formula. You can check the formula in the box. That there's only one way, really, in which you get a number. There's a couple of ways to get a number, but you always get the same number. Anyway, it's when you choose 1, 2, 1, 2. Another possibility is 2, 1, 1, 2. Another possibility is 1, 2, 1, 2. Another possibility is 2, 1, 2, 1. You get plus or minus this quantity here. And this quantity here is you recognize as the determinant of the second fundamental form. At least, when you're in an orthonormal basis, you can interpret this properly because really you need to the shape operator. Never mind. If you're in an orthonormal basis, you can interpret this as the determinant of the second fundamental form, which is the Gauss curvature. So this brings us actually to the way Gauss himself figured out his own theorem, which is he discovered that this particular combination of extrinsic curvatures didn't depend on anything except the intrinsic, was intrinsic. A particular combination of extrinsic curvature is an intrinsic quantity. That's what he discovered. And the reason is, well, the right-hand side, let me just say it again, the reason is the right-hand side is your extrinsic curvature. The left-hand side is something you compute from the gammas, which you in turn compute from the g's. So you have an extrinsic curvature quantity in some way is equal to an intrinsic thing. Okay, so I am a little bit low on time, so I'm going to just talk my way through this. There's no more derivation. Derivation always slows us down. So what I'd like to do is introduce the concept of an isometry. An isometry is a mapping from one surface to the next, or in some cases from a surface to itself, which preserves the metric at corresponding points. So in other words, the metric tensor operates on vector fields, and so you need something to move vector fields around. That's d phi, the differential of phi. So yeah, so I guess the picture is you have a circle, and the picture is this. The picture is here. You have surface prime, you have a metric here, you have a metric here, and you have vectors like this, x and y at p. Over here is phi of p. Here's x tilde, and over here is y tilde. And let me say x tilde equals to d phi acting on x, and y tilde equals to d phi acting on y. And then your formula is that the metric at those corresponding points is unchanged. Okay? So if such a mapping exists, it's called an isometry. It's easy to get isometries. It's easy, but it's not easy. But in any case, if your surface is in R3, it's sort of easy to get an isometry, which is you have one surface here, and then you translate and rigidly rotate the surface. your parametrization of that surface has changed, but intrinsically the surface is the same. And the geometry is the same because the inner product, the external inner product is invariant with these rigid motions. So it pulls back to the parameter, into the parameter domain in the same way. You do have isometries which are not from rigid motions. Here is a nice one. So it turns out the catenoid, which you see right there, is isometric to the helicoid, which is a spiral staircase surface. And there's a natural isometry, which I'm going to play for you in a second. In fact, it's an intrinsic deformation, which makes these, which shows. How do I loop this? Anyway, just do it again. Right? So what you see here is, well, the thing you should focus your eyes on are these squares, right? These are the squares in the parameter plane. And as that motion was happening, those squares were not distorted, right? So this is, and the lengths of those squares are staying the same. The side lengths of the squares are staying the same. Do it one more time. This is evidence that your surface is changing isometrically. The induced metric is changing. But in extrinsic space, that's quite a complicated motion. So extrinsically, you're not doing you're not doing something simple like a rigid motion or translation of the surface. You're really changing it in quite a fundamental way. But intrinsically, as you can see by looking at these squares, the geometry intrinsically isn't changing. So it is possible to have surfaces which are isometric to each other, but not via an external rigid motion. Okay. So there's a whole list of different notions of isometry, and I think, well, these are pictures to ponder, so maybe I'll put this up on a transform, given the lack of time, I'm going to transform this into a supplement. No, in fact, I think I'm going to do this. I think I'm just going to continue with this on Monday's lecture. That's what I'm going to do. Okay, so let me go through this slide, and then we'll consult with Justin, of course, before we do this. But, yeah. Okay, anyway, notions of isometry. Okay, so you have all these different kinds of notions of isometry. So we just talked about extrinsic isometries, or induced by a rigid motion, and then intrinsic isometries. Another example of that is a plane and a non-planar developable surface. So, or for example, maybe I should have put, oh, okay. So here's an example. A cylinder. A cylinder, well, maybe you should think of a cylinder as a wrapped plane. So a giant can have up there. So a cylinder is a plane wrapped around itself. And this thing clearly has some symmetries. I mean, some isometries. Because you can take points and you can translate them up the side of the cylinder. Or you can take points and rotate them around the cylinder by a fixed angle, right? These are motions, these are transformations of the surface of the cylinder, which obviously don't change the geometry, right? Intuitively, that's the case. Okay, but it turns out that I can produce a neighboring surface which more or less has the same kinds of isometries. It's just not a cylinder anymore. Okay, how do I do it? Take a cylinder and let me poke in various directions in some random ways. So this is a cylinder of paper where you've pushed in different directions. Okay, and so now the thing is no longer it's no longer rotationally symmetric in an extrinsic sense because it's sort of jumbled and you've pushed it in random directions, right? But from an intrinsic point of view, this thing is still a flat sheet of paper. And in fact, I achieved that by flattening and putting it down on the plane. So this motion here this motion here, which now kind of looks like this. Right? This motion here is still an isometric motion of this transformation, moving these points to here in this sort of undulating fashion, is still an isometric transformation of the underlying intrinsic geometry, even though it's no longer induced by rotation from outside, because you've broken the outside symmetry. Okay. You have another notion, you have another idea of isometry versus deformation. So you can have isometries where, which is sort of a large scale thing like a reflection. You can have reflections which are, discrete jumps, right? They're a big transformation of the surface. So for example, something like you have this, my so-called amphora surface, which looks like this. Well, in fact, my amphora is going to look like this. Maybe bowling pin is a better. So this is a surface of revolution, which has this particular property. So here's an intrinsic isometry of this, which is like a discrete isometry, and it's a reflection. Put a mirror down the middle and reflect points across. Okay. Reflections are rigid motions in the outside world, and they are inherited by a symmetric object like this shape that I've drawn here. And since the inner products don't change under the reflection, the induced geometry doesn't change. That's an isometry. Okay? So this is an isometry which is sort of, it's induced from the external world, fine, but it's also a discrete isometry. It's one big jump. This point over here gets reflected over to that point there. That's a discrete one. Here is another discrete isometry which doesn't come from the outside world. Again, take the amphora surface and do this to it. You see what I just did? Right here, I flipped, I popped the surface in. So I explicitly made this flat. This is supposed to be very flat. So to second order, it's so flat there that you don't notice the difference between going up and going down. It's like quintic or something like this, right? And so there's no way that the metric, the induced metric, could tell the difference between this surface and that surface because this is somehow so flat here. And also, like the local geometry at every point, the local geometry is unchanged. The inner products are unchanged. So this here is an example of another example of a discrete isometry which is not induced from anything from the outside world. Let me actually stop with my discussion of different kinds of isometry, and we'll continue again on Monday. But maybe the upshot of the take-home message for now is that I'm showing you lots of isometries, but the point that I want to make is that isometries are in fact quite rare. And the reason they're rare is because the surface has to be well adapted to the existence of an isometry. If this is going to have a reflection symmetry, the surface itself has to have some property, some geometry which makes that possible. And from a mathematical point of view, if the Riemann curvature tensor is an obstruction to having, the Riemann curvature tensor has to be the same at two different places. I mean, if you're going to map from this surface to that surface with an isometry that leaves the metric unchanged, then quantities you derive from the metric have to be unchanged as well, including the Riemann curvature tensor. And it turns out the Riemann curvature tensor is like the thing which makes that, which is like the obstruction to construct, again, the obstruction to constructing an isometry. Right? It's the key thing. So what I didn't get to is just a discussion of rigidity theories, like what's isometric to what, when things are, when isometries are non-existent, and so on and so forth. And I wanted to give a couple of rigidity theorems, and one of them was the famous Gauss-Bonnet theorem, which I was going to walk through a little bit, but I didn't get a chance to do that. So we'll do that on Monday. All right, so that's it for today.